Phew, okay, not too bad. But I'm just going through the announcements right now. We have a Gitlit checkpoint on Friday. And Gitlit is one of the most intimidating projects in this class, so we definitely recommend starting early and yeah, getting help in lab if you need it. And then we have 2 quizzes this week, quizzes 5 and 6 on Wednesday and Friday respectively. And we've added the incident report form and shout out form on the front page of the website. So yeah, let's get started. Okay, so today we're going to be talking for the first half a lecture about asymptotic analysis, which is definitely one of my favorite topics in the course, so I hope you all are excited. So in 61BL so far, we really care about writing efficient programs. But so far, all we've really talked about is programming cost. What that means is how long does it take to develop our programs? How easy is it to read, modify, and maintain our code? Okay, but efficiency is a bit more than that. A cool saying is that an engineer will do for a dime what any fool will do for $1. Okay, so now we're going to talk about an aspect of efficiency called execution cost. So there's 2 kind of variants of this. One question is, how much time does your program take to execute? The other one is, how much memory does your program require? So today we'll be focusing on the first question. How much time does your program take to execute? So for a bit of a motivating example, let's say that we want to determine if a sorted array contains any duplicates. So suppose we have the sorted array A, and we want to ask ourselves, are there 2 indices, I and j, such that A of I is equal to A of j, right? So one silly, naive algorithm is we can look at every possible pair of elements in the array, and if any pair matches, we return true, right? Okay, good spotlighting. But is there a better algorithm that kind of leverages the sorted nature? So this is a fun algorithmic problem, so let's stop for like 10 seconds. Just kind of think about this for yourself. Is there a better algorithm than the silly one I described before? Okay, so there definitely is a better algorithm. And one example of a better algorithm is whenever we look at A of I, we're going to look at A of I plus 1. Okay, and the first time we see a match, we return true. And if we've looked at every element in the array, then we return false. Okay, so we have 2 algorithms here. And our goal for today's lecture is to introduce a formal technique for comparing the efficiencies of these algorithms, right? Okay, so let's kind of build some intuition for how we're going to achieve this. So we have 2 algorithms, the same ones described from the previous slide, just kind of copied here and translated into code. Okay, so dupe 1 is that first approach. So what's happening in dupe 1, just so we understand the code, because it's going to happen, or it's going to come up a lot in this lecture, we have 2 for loops here. Okay, and these for loops, in essence, just iterate through every pair of elements in A. Okay, and then every time we have a pair of elements, we say, are you equal? If you're equal, we return true. So that's dupe 1, which is the silly approach. Dupe 2, the more efficient approach, says we'll iterate through the array A, and every time when we're at A of I, we say, let's look at the next index, A of I plus 1. If they're the same, let's return true. Okay, so these are 2 algorithms. And our goal today is to characterize the runtimes of these functions below. Okay, our characterization should be simple and mathematically rigorous, right? These kind of 2 conflicting ideals. And it should show why dupe 2 is better than dupe 1, right? Because it definitely looks better than dupe 1 to me. It seems 1 less for loop, that seems to be a dub. Okay. So the first technique, and I think this is the really intuitive technique, right? Let's use a stopwatch, right? What we can do is I can execute to dupe 1. I'll record how long that takes. I'll use my iPhone stopwatch. And then I'll run dupe 2, record how long that takes, right? Just kidding, the iPhone stopwatch isn't that good. Princeton Standard Library has a stopwatch class that we can import. Okay, so let's kind of see how this would work. So when we're running dupe 1 and dupe 2, we can kind of look at this graph to see how they fare. Okay, So on this left-hand side, it's the time in seconds for the execution. On this right-hand side, it's n, where n, I kind of skip this right here, is the size of this array. Okay? So this graph is really, really important. It's going to come up a lot in this lecture. So important here to understand, the x-axis is n, the size of the array. This axis, the y-axis, is the time it takes. So what we can see here is that dupe2 is much better than dupe1, right? As n gets bigger, dupe2 just destroys dupe1 in efficiency. So looking at technique 1, where we just use a stopwatch, the pros to this technique is that it's easy to measure, right? It's very easy for us to just call a stopwatch. And the meaning is obvious. What I mean by that is if dupe1 takes 40 seconds and dupe2 takes 5 seconds, it's very clear what that tells us. The meaning is very clear. So a couple cons to this approach, and these cons aren't that intuitive actually, is it may require a large amount of computation time. So what does that mean? It may require a large amount of computation time. Suppose we call dupe1 on a really, really big value of n, right? That means we're going to have to run our program for a really, really long time. So it's a lot of computation time. And another not so intuitive downside is that it's a bit inconsistent between different computers, right? Let's say one computer is a bit faster than the other computer, right? Then one computer can say, I think dupe1 takes 14.8 seconds. The other computer says, I think dupe1 takes 14.2 seconds. And now we have these conflicting, inconsistent descriptions of the runtime, right? So these are a couple cons. Okay, so let's try to figure out a better way of quantifying this runtime. So let's move on to technique 2a, which is a preface to technique 2b. And what we're going to do here is count the possible operations for an array of size 10,000. I just randomly chose 10,000. Okay, so what do I mean by possible operations? Looking at this table right here, we're going to say every time I see this operation, I'm just going to keep a tally. Okay, every time I see a less than sign, I'm going to keep a tally, and then we'll keep track of the total number of times that operation has been executed. Okay, so let's first walk through this table, and then we'll kind of talk about the pros and cons. So the first operation, I is equal to 0, it happens once, right? Because we set I is equal to 0 exactly one time, and then we never do that line again, okay? So for the remaining lines, the counts are really hard to compute. Like we don't expect you all to make these count tables, but just accept that it's true, okay? So I'm just going to fill them in quickly. So we can see here that these are really big numbers because n is really, really big, okay? And we have kind of a range here, okay? I'll explain what this range is because I think it may be a bit confusing. So let's look at array axes, okay? We can see the range goes from 2 to 99,000, okay? So the 2 number here, this corresponds to the best case, okay? What do I mean by this? Well, the fewest number of times we can access an array are in the situation that the first time I hit this if statement, it evaluates to true, right? The first time I hit the if statement, if it evaluates to true, we do exactly 2 array accesses, right? That's the minimum number of array accesses we can possibly do, okay? The maximum number of array accesses, what I call the worst case, is if there are no duplicates in the entire array, we exhaust these 2 for loops and we have to return false. Okay, so this is kind of the best case and worst case here. And this will also come up a lot. So yeah, important to understand the behavior of this function depends on the contents of A, right? So the runtime accordingly, or how many counts we have, varies. Okay, so let's move on to technique 2b. Actually, no, we still haven't talked about the good and the bad. So let's quickly talk about the pros and cons to this approach. I said we'll come back here, and we are. So the pros to this approach are that it's machine independent. Okay? What I mean by that is now that we're counting the total number of times of a specific operation, we don't run into the problem from before, right? The problem from before was that computer one could take 14.8 seconds, the other computer takes 14.2 seconds, right? But the number of operations is going to be the exact same on this computer and this computer. So we don't have that problem anymore, okay? The cons to this approach is that it's really tedious to compute. Like, who has any idea where we got this number from, right? It's really complicated, and it's too tedious to even do in practice, right? Another con is that where did we get 10,000 from? Somehow we just randomly decided to use 10,000. So it doesn't really tell us the actual runtime, okay? So let's move on to technique 2B. We're slowly improving. Now, instead of doing 10,000, we're going to say, let's abstract away the array length into a variable n. So instead of having 10,000 as the fixed array length, we're going to say, what if the array length is some variable n? Okay? Now, what that gives us is a new column called symbolic count. Okay? What the symbolic count is, this column is saying, is that for any value of n, we have a range of possible counts, okay? And this column, in my opinion, is much better than this column here. This column only really gives us information when n is equal to 10,000. This column, on the other hand, I can plug in any value of n, and I figure out the exact counts, okay? So we've kind of just upgraded this count column. So the pro to this approach is that now we learn how the algorithm scales. So what does algorithm scales mean? As n gets bigger and bigger, we now understand how the counts change over time. The con to this approach is these numbers, finding a formula is really tricky, right? Like, how do we figure out these formulas? So it's even more tedious to compute, and it still doesn't really tell us the runtime, okay? So let's pause here. That was a lot at once. Let's kind of walk through a quick example. So here's a question for all of you. Suppose we have dupe2 below. Same dupe2 from before. Let's try to fill out this table, okay, to find the symbolic counts and actual counts when n is 10,000. Okay? I recommend starting with the symbolic counts and then trying to figure out this entry after. So we'll stop here for around a minute and just, yeah, try figuring out some entries in this table. Okay, I think that's enough time. So let's see the answers. Okay, so we can kind of see the symbolic count table right here, the column, and for n is equal to 10,000 as well. I'm not going to go into the specifics of these examples. If you guys do want to check your work or you got a different result, we can come back at the end of lecture and we'll go over it from there. But I'll leave it up for another 5 seconds just to see, just for y'all to see. Okay. So I think a takeaway from this example, it's pretty tricky to come up with this table. Okay, but if we have this table, it gives us a lot of information about dupe 1 and dupe 2. We can even say that I think dupe 2 is better than dupe 1 with these tables, right? Let's try to think about why we can make such a claim. So there's a few reasons here. Let's go from worst to best, okay? So the first idea here is let's look at this column right here, okay? And let's kind of look at the less than operation. Notice that for less than, for dupe 1, it's 50 million times we have to do the less than when we do dupe 1. On the other hand, for dupe 2, it's only 10,000. So we can see that dupe 2 is so much better in this specific less than operation count, okay? But that's not really that great of a metric because we didn't really consider how both algorithms scale over time. We just said when n is 10,000, dupe 2 happens to do better in regard to less than. It's very specific. It's not that great of a metric. So let's improve how we say dupe 2 is better. And what we're going to say here is that the algorithm scales better in the worst case. Okay? What I mean by that is when we're looking at dupe 2 and we're considering the worst case behavior of less than. Okay? Notice that dupe 2 only has n times the less than operation is called. On the other hand, when we look at dupe 1, it has this many times the less than operation is called, right? So we can see that n is so much better than n squared plus 3n plus 2 divided by 2, right? Because it's smaller and we want to be more efficient, okay? An even better answer than this one, and this answer may not be too intuitive, is that parabolas grow faster than lines. What I mean by that is we can kind of look at this n squared here, right, versus this n here, and we can say that over time, n squared kind of looks like that versus n looks like that, right? So this one will do worse over time. And we'll talk about this one a bit more in the next couple slides. Okay, so we've kind of touched upon this idea of asymptotic behavior. And this slide is really, really important. It kind of sets the framework for asymptotics going forward, okay? So when we talk about functions, we really only care about asymptotic behavior. That is what happens for a very large n, okay? What I mean by that is in the real world, we have programs that create a simulation for billions of interacting particles, or a social network with billions of users, or we log billions of transactions or encode billions of bytes of video data. What I mean by that is when we talk about functions, we want to consider the case when n is really, really big, because that's what's happening in the real world. And that's where efficiency really matters the most, right? So let's kind of go back to the lines versus parabolas question. So suppose that we have two algorithms that zerpify a collection of n items. We've purposely said zerpify because who cares what zerpifying is? They just do something called zerpifying. It doesn't really matter, okay? We have one called zerp1 and zerp2. Okay, zerp1 takes us 2 times n squared operations. Zerp2 takes 500 times n operations. Okay, and what we'll notice here, this is a really, really important slide. When n is small, right, when we look at this graph right here, the bottom is n, right, this axis. When n is small, we can see that zerp1 might be faster, right? We can see that zerp1 is doing better, because zerp2 has this 500 term that makes it pretty bad when n is small. But as the data set size grows, notice how zerp2 does better and better, okay? And this is why asymptotic behavior is really important. We only really care about when n is really, really big. So this idea that zerp1 happens to be better when n is small doesn't matter too much to us, because we care about the situation when n is really, really big, because that is what asymptotic behavior is, okay? I'm just going to leave this slide up for another 5 seconds because I think it's really important to just try to soak this in. Okay, yeah, let's keep going. So we've touched upon this idea of a shape of a runtime function. Okay, and we're going to call it the order of growth. We're going to formalize this a bit more soon. So this idea of looking at a function and figuring out its order of growth is dramatic. It often determines whether a problem can be solved at all. So looking at this little chart below, this gray bar gives us possible orders of growth. Okay? And what we can see is that when n gets bigger, some of these slower orders of growth aren't even possible to run on a computer. They're so slow, right? And looking back to the previous example, when we have n and n squared, and we have n is really, really big, notice how n does so much better than n squared, right? Just kind of reaffirming what we saw between dup1 and dup2. Okay, so let's go back to our initial goal of duplicate finding, right? Our initial goal of duplicate finding was to somehow characterize the runtimes of the functions dup2 and dup1. So far, we've said dup2 is better than dup1, but we haven't done so in a way that's simple, and we haven't done so in a way that's mathematically rigorous. So that's the next problem that we're trying to address. Okay, so I think we're doing pretty good on time. Let's keep going. So kind of touching upon the same idea from the previous slide, we want our characterization to be simple and mathematically rigorous, okay? The reason it isn't simple is that this table is not simple at all, right? These tables are so complicated. They're huge, they're bulky. And the reason it's not mathematically rigorous is right now, all that we're saying is that the left function is like a parabola and the right function is like a line, right? So let's try to make it more simple and more mathematically rigorous. And in the next few slides, we're going to start off by making it more simple. Okay, so the first simplification is we had this table before that had the best case behavior and the worst case behavior. Let's only consider the worst case behavior. Okay, so why can we make such a simplification? It seems like we're losing a lot of potential cases. So one justification for why we can sometimes make this simplification is that when we're comparing two algorithms, oftentimes we only care about the worst case, okay? For instance, when we're looking at, this is dup1, right? This is dup1, two for loops means dup1. Looking at this example, when there are no duplicates, right? This is the worst case behavior because we have to go through both for loops. Notice that this is the situation that takes a lot of time, right? When there's no duplicates and we see the worst case behavior, this is the biggest performance difference, okay? So just to recap once more, we only sometimes care about the worst case because the worst case behavior is when we see the biggest performance difference between two algorithms, right? Okay, so to motivate the next couple simplifications, let's consider the algorithm below, okay, which we've represented with this symbolic count table. Okay, what do we expect to be the order of growth of the runtime for this algorithm? And we have four options here. Okay, let's give around 20 seconds to think about this one. Okay, so yeah, feel free to send it in the chat what you all thought, just to like kind of voice things out. We can get a gauge. Okay, so the answer here is cubic. And the quick argument why cubic makes sense is when we're looking at this table, let's break it up into each operation and how many times that operation occurs. And we're going to get this following sum, okay? Taking a step back, if we have the less than operation that takes alpha nanoseconds, If greater than takes beta nanoseconds and the AND operation takes gamma nanoseconds, what we'll see is that less than happens this many times and takes this long. Greater than happens this many times and takes this long. And happens this many times and takes this long. So the total number of operations we do is the following sum. And what we can kind of convince ourselves of, this sum is dominated by this term right here. Because as n gets really, really big, this term scales more than the other terms do, right? It's much larger than the other ones. So this point is really fundamental to asymptotic analysis. So just pause for a couple seconds and try to soak it in. Okay, let's keep going. So with this motivation, we can see some more simplifications, okay? The first simplification is that we can restrict our attention to only one operation. What I mean by that is, going at this example, notice that we only really looked at greater than, right? So in a similar light, let's pick one operation to act as a proxy for the overall runtime, okay? So looking at the table, notice that all of these 4 operations all have an n squared term. So in essence, we can choose any of them. Let's just choose increment, okay? So this idea is called our cost model, and it's one way of figuring out a possible order of growth, or getting there. We're getting in the right direction. Okay, so that's the first simplification. We're picking one operation and ignoring the other ones to make life simpler for ourselves. Okay? The next simplification is, let's ignore lower order terms. What I mean by that is, when we have this expression right here, notice that n is a lower order term compared to n squared. And what we've convinced ourselves of from the previous example is, in the long term, n gets dominated by n squared, right? N squared is much bigger. So we can kind of ignore this because it's not as big, okay? And the last simplification, this one sometimes is a bit iffy for students, is we can ignore multiplicative constants, right? Looking at n squared over 2, let's just get rid of the divided by 2. So why can we do this? Well, what is order of growth? Order of growth is the shape, right? It's the shape of the curve. If I have a multiplicative constant, it's not really affecting the shape of the curve, right? It's scaling the curve, but it's not affecting the shape. And when we talk about order of growth, we only care about the shape of the curve as n gets big. And a multiplicative constant isn't going to affect the shape. So kind of looking at all of these simplifications on one slide, what we've done in a really cool fashion is we've taken this complicated table and we've reduced it to this one smaller table that has a much simpler expression, okay? And how we achieve that is with 4 simplifications. Let's quickly walk through them. The first simplification is we only consider the worst case, right? So we've gotten rid of all of these ranges and we're only looking at the right-hand side. The next way we simplified it is we picked a representative operation, right? In this example, we picked increment. Then what we did is, once we had this expression right here, we reduced it by ignoring lower order terms like pi by 3 and pi by 2, and ignoring multiplicative constants, pi divided by 2, and we got n squared. We were actually looking at this example, but it works for less than as well. Okay, that was a lot at once. So yeah, we've successfully gone from the symbolic count table to a smaller order of growth. Okay, let's pause for a bit, and we're going to move on to talk about some bounds. Okay. Whew. Okay, let's keep going. Hopefully asymptotics is fun. I'm having a lot of fun. I hope you all are too. So the next couple sections, we're going to be talking about some bounds. And up to this point, it's a lot of motivation, but the next slides are going to be very applicable to the problems you'll be solving in this class. So let's first formalize the order of growth, what we've learned so far. Okay, if we have some function r of n, let's apply the last two simplifications, which were ignoring lower order terms and multiplicative constants, to yield our order of growth, right? That's kind of what order of growth is to us. For example, if we have some function r of n, which we can express using this formula, we can say its order of growth is n cubed as we get rid of this lower order term and we say pi by 3, right? Okay, so we're going to move to a more formal notation called big theta. Okay, and when we look at big theta, the math may seem a bit daunting, but the idea is exactly the same. What I mean by that is instead of using order of growth, we're just going to put in big theta. Okay, so let's first gain a bit more comfort with order of growth with the following exercise. So I'll give you guys around 30 seconds, and let's say that we have each function below. So what is the shape of each function for a very large n? In other words, what is the order of growth? Okay, so just try to think about a couple of these entries in this table. Yeah, so around 30 seconds here.
I'll stop.
Okay, I think let's go over it. So here are the orders of growth, and all we're really doing is ignoring the lower order terms and ignoring any constants, multiplicative constants, that is. Okay, so I think this exercise is good because we're going to translate very easily to big theta, okay? We had these orders of growth, and now all we're going to do is if we have some function, r of n with order of growth f of n, we're going to say r of n runs in theta of f of n, okay? So this function here runs in theta of n to the fourth. This expression, this function runs in theta of n cubed, and so on. So we haven't done any new math. We've just kind of used a new notation. Okay, so this is how we've expressed the runtime of the following functions, okay, using a theta notation. So a more formal definition, I think this definition is sometimes a bit confusing. So if it goes over your head, totally okay. For the mathy people out there, this may make sense. Suppose we have some function r of n that runs in theta of f of n. What this is officially saying mathematically is there exist positive constants k1 and k2 such that r of n is bounded with the lower bound of k1 times f of n and an upper bound of k2 times f of n. Okay, so if this doesn't make sense, totally okay. We'll look at a quick example. Suppose that we have this function r of n, and f of n is n squared. Okay, the reason we can use a theta bound here is I can say that k1 is 3, k2 is 5, f of n is n squared, and it actually bounds r of n, as we can see in this visualization. Oh no. That visualization worked like very recently. I have no idea what just happened. Okay. Okay, now it's working. So I don't know what happened there. But anyways, looking at this example here, what we can kind of see is that this red curve in the middle is the actual function, okay? These two black curves on the outside, these two black curves kind of bound the red curve in a way, okay? So we can kind of think about them as a lower bound and upper bound respectively, right? So this is the same exact example, and we can see since this red curve is always between these two black curves, it runs in theta of n squared. Okay, that's the intuitive visual way of looking at a theta bound. But this may be a bit confusing, so I have a slightly more intuitive way of how I like to think about theta bounds myself. Okay, my intuitive definition is that if I have some function r of n and it runs in theta of f of n, what this is telling us is that it will always take f of n time. In other words, every time I execute the r of n program, we are guaranteed it'll take f of n time. That's how I like to think about a theta bound. Okay? So if I look at this for loop, every time I execute this for loop, it's always going to take me n time, right? So we can say it runs in theta of n. So that's a way of thinking about a theta bound. If a block of code always takes the same amount of time, we can give it a theta bound. That's all a theta bound is. Okay? So let's keep going. Looking at the symbolic count table from before, we haven't really changed anything. All we've done is we've replaced the order of growth with a theta bound. Okay? So nothing really new mathematically, just different notation. So two new bounds that we'll talk about are big O and big omega. And I think, yeah, we still have some time left, so we're doing well on time. I'm going to plug in my laptop. It's almost dying. So you all get a 30-second break. Okay. So two more bounds we'll discuss. Let's start off with the big O bound. Okay. So just to recap the big theta, we used a big theta bound to describe the order of growth of a function, right? So big theta can kind of be thought about as equals in that regard. So big O can be thought of as less than or equal to. Okay. So if we have some function, let's say we have some function right here that runs in n cubed plus 3n to the fourth, we can say it's theta of n to the fourth. It's equally valid to say it's big O of n to the fourth because it's less than or equal to n to the fourth. It's also equally valid to say it's big O of n to the sixth because it's less than or equal to n to the sixth, right? It's also valid to say it's big O of n factorial, right? And it's also valid to say it's big O of n to the n factorial. So whenever we have some function, a valid big O bound is any bound that's kind of bigger than the function. That's how I like to think about it. Okay? But you may be saying, hey, Sohum, this bound, all of these bounds aren't that good, right? They don't tell us that much about the function, which is true. So what we can say is that this bound is the tightest big O bound. Okay? Because we can't go any smaller than this bound. It's the tightest big O bound that we can possibly have for this function. Okay? So I think for the sake of time, I'm going to skip the formal visualization. But when we look at the formal definition of a big O, it means there exists a positive constant K2 such that R of n is less than or equal to K2 times F of n. Okay? All that this is saying is that R of n is always less than or equal to F of n. Okay? So my intuitive definition, which I like a bit better, is when we have R of n that runs in big O of F of n, what this means is that R of n will never be worse or slower than this bound. Okay? And I like to think about a function is bad if it takes a long time to run. Okay? So let's look at the example dupe2. Okay? Quick question for all of y'all. I'll give y'all around 15 seconds. What is the runtime of dupe2 with a tight big O bound? Okay? This is a really good problem, so actually try to pause and think about it for 15 seconds. And here's like an intuitive definition to try to lead you on the right track. Okay, so send it in the chat if you had any guesses on what a tight big O bound could be here. Hopefully some people are using the chat. Okay, I think I see the chat. So the answer is big O of n, okay? The reason, I think the line of reasoning is very important to understand here. The dupe2 function, in the worst case, what will happen is that there's no duplicates and will iterate through the entire array and will finally return false. In that worst case behavior, we take n time, okay? So what we can say is that the function r of n will never be worse or slower than n. There's no way we can be slower than n, right? So the tightest big O bound is big O of n. A valid big O bound is big O of n squared, but the tightest one is big O of n, okay? So that's how we can kind of think about big O bounds. So let's jump to big omega. So looking at big omega, whereas big O can be thought about as less than or equal to, big omega, with this little omega sign, can be thought of as greater than or equal to, okay? So if we have some function n cubed plus 3n to the fourth, all of these bounds are true. It runs in omega of n to the fourth, omega of n cubed, omega of n squared, omega of n, and omega of 1. The reason is that this function is greater than all of these runtimes, right? So this is what a big omega bound is, okay? A big omega bound is saying, if I have some function, I'm guaranteed that my function is going to be greater than this bound, greater than or equal to it, okay? But again, the tightest big omega bound is going to be this one because we can't go any bigger than this bound, right? Okay, so this is the tightest big omega bound, but all of these are valid. So the formal definition here, it's exactly the same as omega. It's just kind of like symmetrically opposite, right? If we have some function r of n that runs in omega of n, it should be f of n, but same idea. What that means is there exists positive constants k1 such that k1 times f of n is less than or equal to r of n, okay? So this is our way of looking at omega. Again, in the previous examples, I put f of n here, but same idea. Okay, so my intuitive definition of big omega is if we have some function r of n that runs in omega of n, what that is saying is the function r of n will never be better or faster than this bound. So again, let's pause here, 15-second question. Let's say that we have dupe2, and we want to figure out what is a tight big omega bound. Okay, so yeah, take 15 seconds to try to figure out a tight big omega bound. Okay, I think that's enough time. So the answer here is going to be omega of 1. The reason for this is when we think about omega, we want to find a bound that the function r of n can never do better than. Okay, so we want to consider the best case behavior. The best case behavior of dupe2 is when A has the first two elements that are exactly the same. In that scenario, this if statement is true, and we return true immediately. In essence, we've done a constant amount of work, right? We've done a constant amount of total steps. So what we can say is that if the best case behavior is constant time, our function r of n can never do better or faster than constant time. So a tight big omega bound is omega of 1. Okay, so let's kind of do a quick summary of all of the stuff we learned. we've talked about big theta, big O, and big omega. Okay? The informal meanings for all of these is that for big theta, the order of growth is f of n. For big O, it means the order of growth is less than or equal to f of n. And for big omega, it means that the order of growth is greater than or equal to f of n. Okay? So if we look at some families, if I ever have some function that runs in theta of n squared, here are some possible functions that could run in theta of n squared. We have n squared over 2, 2n squared, and n squared plus 38n plus n. Okay? If I have some function that runs in big O of n squared, some possible functions are n squared over 2, 2n squared, and log n. Okay? Note all of these functions are less than or equal to n squared, right? Similarly, if I have some function, n squared over 2, 2n squared, or 8n squared, or 8n to the fourth, we can say these all are omega of n squared. Okay? So that was a lot at once. I think, I'm not sure if we have any time. Zoe, how are you feeling on time?
I could definitely use a full hour.
Okay,
so
let's stop here then. So yeah, unfortunately we won't get to the iPad demo, but that is all on asymptotics. So I think let's take a 5-minute break and try to come back at around 4:04. Okay. And if y'all have any questions, I'll be here for like the next 5 minutes just to ask any questions out loud. So yeah, feel free to like raise your hand for the next 5 minutes and I'll take some questions.
Yes.
Yeah.
So earlier you showed a table of asymptotics and you said that the constant of n log n was 20 seconds on 10 to the 6.
Oh. Somewhere back here, right?
Yeah. Yeah,
Here?
like, yeah, on 10 to the 6, n log n on 10 to the 6 is 20 seconds. But shouldn't it be closer to like much less than 1 second?
It shouldn't be less than a second.
Well, 10 to the 6, but computers do 10 to the 9. Computers do 1 billion operations a second.
Okay, so you think it should be less than a second?
Yes. Well, computers do 10 to the 9 operations per second, right? Which means that 10 to the 6 are much smaller.
But if it takes 1 second for n, how are we going to be doing less than a second?
Yeah, that's what I'm saying. I'm saying n is also wrong.
Okay. I think this table might just be a bit old. I think that's the main reason.
Oh,
yeah.
Okay, I see.
Yeah. But yeah, the idea is like the same. The table just from like a little back in the day. We didn't update it. So apologies there. Okay. Any other questions? I'm just going to go back to where we were. Okay. Yeah. Okay, I'd say we still have a few more minutes. So try to take a break. We have a lot of exciting information coming. So yeah, take this time.
So for this, thanks, Sohum. So for the second half of this lecture, we're going to be talking about different ways that we organize information that's stored and then moving forward with how we're actually implementing all of these different structures that we're talking about. So first, we are going to start with trees. So what is a tree, right? Trees are a naturally recursive representation of data, of information, that has a clear hierarchy between objects, that has, quote, more than one recursive subpart for each instance. Really, the most important part of that is the idea that if we take some branch of a tree, that branch is a tree itself. So we'll define a couple of terms. So a tree consists of a set of nodes. So those are the vertices or elements in our tree. We call them nodes. And then a sequence of edges that connects our nodes together. And the most important constraint for trees is that there must be exactly one path between any two nodes. There cannot be more than one path, unique path, between any pair of nodes that we select in a tree. So we'll talk about what that looks like and what that means, especially in future labs. But let's look at, let's think about some examples. So can we get some examples in the graph or in the chat of what something that would be a naturally tree representation would be? Trees in real life, right, are upside down, but have a similar branching structure. A family tree is a great example. Let's get one more from chat. A binary search tree, a factor tree. Okay, I see lots of people, being a little smart with that. Files is exactly what I was thinking about, though. In your device, your file structure is organized as a tree. So now a new definition, rooted trees. A rooted tree is any tree where we've chosen one node as the root. So basically the start, the top of the tree. Every node except for our root has exactly one parent, or there will always be one parent. There cannot be more than one parent. And the parent is the node that we would encounter right before encountering the node we're talking about. So the node one step back on the path from our root to the node that we're walking to. A node on the bottom, right? So one of these nodes floating around here would be a node referred to as a leaf because it doesn't have any of its own children. So for each of these examples right here, we have A being the root of its own tree. We can see that in this example, B is the child of A, and C is the child of A if we're rooting it at A. And then for this third example, A is the parent of all of these children below it. One moment. Sorry. So the A is the parent of the universal parent of all of these nodes. And more importantly, with the recursive definition, if we step down, we can see that B is the parent of all of the nodes below it as well, which are all leaf nodes. So now we're going to step through some orderings or some traversals that are very common in trees. So the first traversal that we're going to talk about is level order. And when we talk about level order, we view it as really like how we would read in English. So starting from the top of the page or the tree, moving from left to right, and then moving down one level after we hit, our rightmost edge each time. So let's get in chat some suggestions for what you would think this the level order visit order would be for this tree here. What order would we visit them in? Yes, I'm seeing a lot of correct answers in the chat. I'm also seeing someone say, this seems pretty hard to implement. I would say in general that level order has a less natural implementation than the other traversals we'll see, and we'll talk about that especially in the labs where you'll implement these. So yes, the most common answer I was seeing in the chat was correct. Basically, what we want to do is step through level by level. So for the first level, we move from left to right, so we get D. The next level, we move from left to right, so we get B and F, and then we move through all of the leaf nodes from left to right. And so that's why this is level order. Okay, so now we're going to move to a different type of traversal, which is a traversal called depth first traversal. So basically what we're going to do is hopefully descriptive in the name of the traversal. But for each path that we walk down, we want to go to the farthest depth we possibly can before moving outwards. So in the last traversal, right, we were going in layers in the way that we read English. In this one, we want to follow a path all the way down. So there are 3 different types of DFS, depth first search, that we talk about: pre-order, in-order, and post-order. So basically with all of these, with those 3, pre-order, post-order, and in-order, the question is, when do we visit the node, right? Because so we're going to step on or step through each node some number of times, right? At least twice. Because we're going to step through it and then step back through it, with leaves being the exception there. But what does visiting it mean? So when we visit a node, that means that we are actually processing the node that we are stepping on. So the difference between pre-order, post-order, and in order is that we are going to visit the node at different times when we're stepping over it. So in pre-order, what we do is we visit the node as soon as we step onto it, and then we traverse its children. So that's why we call it pre-order. We're visiting the node before we do anything else. So we have some pseudocode here of what this traversal would look like. If it's null, right, our base case, but then so our visit here is print, just displaying our tree visually. So we would print the key, visit it, and then we would traverse to the children. And it's canonical in this course to visit the left before we visit the right. So this would be our pre-order traversal, and I want to step through it quickly first. So we would enter our tree at the source or the root, which is D. That is where our tree is rooted. And remember, we're visiting our node before we step to any of its children. So the first thing we would do would be display D. We would then first visit the left child of D. So we can step down and we see B. Now we've stepped onto B. We're visiting B because with pre-order, we visit B before we step to any of its children. And then the first thing we'll do is step to its leftmost child, which is A. Visit A, which for us is printing, and then look at its left child. Is there a left child? No, A is a leaf. That means, is there a right child? No, A is a leaf. So that means that we have finished that path of execution. What do? We step back up 1 recursive frame, back up to B. Where were we in B? Okay, we had just processed the left child, which means that there's 1 more recursive call to the right child. So we'll step down to the right child. This is our first time stepping into C. So that is when we'll visit C, and we'll do the same checks again. C is a leaf. There's no more for us to go, so we'll step back up. Now at B, we've processed all of the children, right? We've executed all of the code. So we're done processing B. We can close that recursive frame and step back up 1 more time. Now we're back all the way up at the root, and we're going to execute the same exact algorithm on the right-hand side of the tree. So we're now executing the very last line of code for D. So that's how we're going to get F, E, and G at the very end. Okay. So this is depth first search pre-order. Now we're going to do depth first search in order. So the difference between pre-order and in order is that in order traversal, we're going to traverse the left child first, then visit the node when we step back to it from visiting the left child, and then we will traverse the right-hand child. So now in the chat, I'd love to see your suggestions for what in order would be for this tree here. DFS in order. Great, getting lots of suggestions in. So I saw some correct answers, and the reason why the first thing that we'll execute is A is, remember, the first thing that we're doing is stepping all the way to the left. We're executing all of the recursive calls to the left before we're ever visiting our node. We'll step through nodes, right, when we're traversing to their left child, but we won't visit them, which for us is printing. So that means we'll start at D. We will, do the null check, but then recurse to the left. At B, do the null check, recurse to the left. Process A, we realize, okay, there's no left child, so there's nothing to do for that recursive call. We will print out the key, look to the right, not see anything, it's a leaf, and step back up to B. Now that we've stepped back up to B, we've already processed B's left-hand children, right? So that means it's time to visit B, because we want to visit in between the left child and the right child. So we would print out B and then recurse to the right-hand side and do the same process for C, eventually stepping all the way back up to D and doing the right-hand side. So this is depth first search in order traversal. And I keep, really emphasizing the names for these because, again, it's for the past two that we've talked about and the next one that we talk about are all depth first search traversals. And the only difference is when we are visiting the node. And so that's why we're using these two different terms. So now we're talking about depth first search post order. And you might guess that if, first we visited before we did left or right, then we visited between left and right. So the third option is visiting after we see the left child and the right-hand child. So we're going to traverse left all the way, we're going to traverse right all the way, and then we are going to actually visit our node. So again, I'd love some suggestions in the chat of what you think the DFS post order would be for this graph, for this tree. Great. I'm seeing lots of great suggestions in the chat. So yes, I saw lots of correct guesses in the chat. So basically what we'll do is we'll start at D. We'll traverse to the left because, again, it's still we do left before right. So we look to the left, we see B. Okay, B still has children, so let's traverse to the left. We reach A. A is a leaf node. We try recursing to the left, there's nothing there. We try recursing to the right, there's nothing there. So that means now we visit A. So that's why A is the first node that we print out. Then we're done with the recursive path starting at A, so we can step back up to its parent. Its parent is B. We've already assessed the left-hand children of B, and so now we look at the right-hand children. We look at C. We do the same analysis. It's a leaf. There's nowhere more to go. So we can visit C, print out C, and then step back up to B. We've now visited all of B's children. There's no more work to do for B. And so that means it's now time to visit B. So that's why B is the third item that we would print out. We then step back up to D. And for D, we've only looked at the left-hand side. We haven't looked at the right-hand side yet. So that means we're not going to visit D yet. We're going to visit all of its children before we visit D. So we'll step down here, do the same process, walk all the way to the leaves, print out the leaves before walking back up and finally visiting our root node as the very, very last node that is printed out. So now, just as a quick aside, this is more of an exam tip really than anything. If we ask you to execute some tree traversals quickly, it can be a little bit cumbersome to step through the full algorithm if you're, a little stressed, time constraint, whatever, on an exam. So a useful trick is you can draw this line starting from the root, going to the left around the entire graph. And the pre-order, post-order, and in-order traversals will depend on what side of the node you are passing on in this traversal. So for pre-order, like as soon as you are on the left-hand side of the node, basically that means we're passing by it for the first time. With pre-order, we visit before we visit either of the children. So that's when we would denote, whatever node we were walking past. For in order, we would visit it whenever we hit the bottom of the nodes. And that's because, again, we want to visit our node in between its two children. So we could see that, we would go up in between our children nodes here, and that's when this node would be displayed. Our 5 would be displayed in between, the 7 and the 8. And then for post-order traversal, it's very similar to pre-order, but it's on the right, right? We want to visit our node once we've visited all of the rest of its children. So for 2, it would be when we finally made it back up to here on the right, when we visited all of the other nodes. So this is a great trick to use if you're just trying to move a little bit quicker in an exam and trying to figure out what the traversal would be. And I just noticed I forgot one of these little icons. There should be an icon on the right-hand side of this 3, because this is an example for post order. So we would put our little save icon on the right-hand side of all of our nodes. Okay. So now what good are these traversals? We kind of hinted at this at the beginning when I asked what tree structures we see commonly in life, but pre-order traversal is one of the most straightforward ways of printing out your entire directory. So if you have some sort of file structure that looks like this and you wanted to just, for example, print out all of the string names, the easiest way to step through all of these would be a pre-order traversal that that could be indented and nicely formatted based on the recursive level. So these are algorithms that you will actually see in real life. We will talk about topological sort as something that will come up, but if you'd like to, as an extra thing after lecture, you could look that up. If you're planning on doing interviews for technical things, topological sort might come up. So just as a soft hint that might come up in your future, so it might be nice to look at. So then where are we going from here? What more are we doing? Today we talked about trees as a simplification of a larger network of data that has some sort of relationship between them, right? Where we had this constraint that each node cannot have more than one path from it to any other specific node. So moving forward, we're going to do a little bit more with breadth first search, which is the very first search that we talked about, right? We will go into that a little bit more in depth. That was the first search that we talked about. But then more excitingly, after that, we're going to move into graphs, which are a more general version of trees, right? We can represent a lot of information in trees, but anything that we can represent in trees, we can represent in graphs. So these ideas are going to move forward, and we're going to learn a whole bunch of really cool graph algorithms that are used really commonly in everyday life and a lot of the tools that you use that will be very, very similar to these traversals, just working through a graph. Okay, so now we're going to move on to the second segment of the second half of lecture. This will be a little longer and perhaps a little bit denser. So take 15 seconds to stretch your arms or move around if you would like to, or have a sip of water. And then we are going to dig into disjoint sets. And I guess I will say, as an aside, in these 15 seconds, not that there's very long, right? That disjoint sets are fun because it's one of the first new data structures that we're introducing in this course, right? We talked about trees, we talked about linked lists before them, and we talked about arrays as well. And we can see kind of a clear relationship between linked lists and trees, right? Linked lists are a simplification of trees where each node is only allowed to have one child, right? And so we see a lot of relationships between these. And now we're going to take this idea of connectivity, so right, where trees, linked lists are data structures that have nodes that are connected together. And we're going to represent that more directly. Okay. So what sort of problems are we curious about? We are going to be talking for the rest of this lecture about connectivity as it's changing. So that's what dynamic connectivity means. It's basically if you have two sets of elements, right? Let's say I have red balls and blue balls, and I can change the color of my balls. How can I represent, right, when I take a red ball and turn it blue and put it in this other set? So we still have disjoint sets, but we're moving elements between them. Then also, how do I represent that if I make all of the balls purple and put them all together, right? So there are lots of times where we're going to want to have disjoint sets of information, but then still be able to move individual data items between them. And this is something that disjoint sets are going to help us do very quickly. So first, we're going to talk about the general data structure, and then we're going to do a couple of improvements together. The first being quick find, then quick union, and then weighted quick union. Then at the very end, hopefully we'll talk about path compression a little bit, but that's more 170 type stuff. So it's a little bit out of scope, but it's very interesting to talk about if we have time. And I'll also make sure that the slides stay in there. So if you're interested, you can always look at those slides to understand path compression a little bit deeper. So now at a more meta level, we're going to do this in this lecture and in the coming lectures, that our goal moving forward will be refining different data structures. So in the next couple of weeks, we are going to talk about classic solutions that other people have come up with to really interesting problems that have an emphasis on the implementation of the data structure in the actual algorithm itself. So we're going to talk mostly about sets, maps, and priority queues as data structures that will come up. But this is just a general framework that we are going to be working through to large degree for the rest of the course. So today we are going to talk about disjoint sets as a data structure. And what we're going to do is we're going to step through together, seeing how a design can evolve from a basic or naive initial implementation to something that's more sophisticated. And we're going to use all of those fun tools that Sohum just taught us to help try and understand some idea of better implementations versus others, so that we can use Big Theta notation to say, this is about how long this implementation will take if you're using it in this setting. This is how long this implementation will use. So we're going to use these tools to have a concrete understanding of when we want to use certain implementations versus others. So we like to say that in a lot of ways, this is an image of Plato's allegory of the cave, that for the folks inside of the cave, for everyone using our data structures, they don't know about the outside world. They don't know about the complexities and dangers and runtime and whatever that's happening out in the real world of the implementation. They just know, okay, I have add last, I have add first, they will work, and they should take about this time. They don't know anything at all about how it's actually implemented. So moving forward in this course, we're going to spend a lot more time thinking about this abstraction barrier and thinking about what do we want our users to be able to, see, what behavior should they expect, what runtime should they expect, and we want to try and keep a firm abstraction barrier between those goals and between the scary outside world where we're manipulating pointers, dealing with the underlying implementation, making all of the design decisions, basically. So now we're going to define two operations on a disjoint set. So these are the two methods that you would be using in general when interacting with the disjoint set. So we can think of this as the ways that we could actually use it. So the most important is the ability to connect two items, right? We have to have some way of representing these two items are in the same set. And then we want to be able to check that data that we've actually stored. So the other piece is checking, I have two items. Are these two items connected? Are they in the same set? Moving forward for the rest of this lecture and more generally, we'll use integers to represent items, but we could be talking about all different sorts of items to go in these disjoint sets in general. So now let's just walk through a quick example. So let's say that we connect our two countries, China and Vietnam, and then we also connect China to Mongolia. If we ask the question, is Vietnam connected to Mongolia? Well, via the transitive property, right, we have a path that we could walk through, right? There is a way to start from Vietnam and end up in Mongolia by only taking valid edges. So basically, pieces that are actually connected together. So that's why this would return true. So now let's connect the US and Canada. If we were to ask, is USA connected to Mongolia? Well, USA is over here. The only thing it's connected to is Canada. Canada doesn't connect to anything else there. So we're kind of out of luck there. And in the same way, if we come over and look, is Mongolia connected to the US? Well, we have one path that we can walk down, but none of those countries are connected to the US. So that means that is connected would return false. We've never connected anything that the US is connected to anything that Mongolia is connected to. So now let's imagine we have some, really fast new transportation method that connects the US to China. If we were to ask now, is the USA connected to Mongolia? The answer would be yes, because we would look at everything the USA is connected to, and we would ask for all of those countries, is this country connected to what I want to get to, or something that could get me to what I want to get to? So for us now that we've added the Hyperloop, this will return true. So these will be useful, like these meaning this data structure will be useful in a couple of different things, right? You could use it in computational chemistry if that's something that you're interested in. More concretely, in this course, we will be using it in just a few weeks to actually implement some to implement some algorithms. It'll be really important in a few things that we do. So this data structure very concretely will allow us to solve interesting problems in much more efficient ways. Okay. So now we are moving away from, items or countries to some sort of, arbitrary or less arbitrary data set. For us, it's going to be integers moving forward. So now we can say that we can declare some number of items in advance, which is what this ds equals disjoint sets 7 means. That means we are creating a disjoint set that has 7 items, and when we start, everything is disconnected. So if we were to connect 0 and 1, it would draw this line. Then connecting 1 and 2, right, would draw this line. 0 and 4 going down. Then finally 3 and 5. So now we can see that we have 3 connected components. So that a connected component is any component where any one element in the component can access every other element in it. So if we were to ask, is connected to 4? Well, we'd look at where 2 is and we'd say, is 4 in this connected component? Yes, it is. So 2 and 4 are connected. Is connected will return true. However, if we asked, are 3 and 0 connected, we can see that 3 is in this disjoint set and 0 is in this disjoint set. There's no connection across them. And so that means that they are not connected. So is connected would return false. So now we add another edge here. An interesting question for you in the chat. Did this change the number of connected components that we have? So adding this new edge, how many connected components do we have? Any guesses in the chat? Yes, so we still have the same number of connected components. There have not been any changes because connecting the number 4, the item 4 to the item 2 functionally does nothing because 2 and 4 were already in the same connected component. They already had access to each other. So adding this edge in real life didn't really do anything. But now if we add a new edge from one connected component to the other, for example, between 4 and 6, we can see that this did make a change and that 6 is now accessible by all of the items in this connected component, but still not accessible to 3 or 5, which are in their own little universe. So now if we were to connect 6 and 3, now 3 and 5 are no longer in their own little universe. They're connected to 6, which means that for any arbitrary item in this set, we could reach every other item in the set. For example, let's say if I wanted to go from 1 to 5, I could go to 2 to 4 to 6 to 3 to 5, right? Every item here is connected to everything else by at least one valid path. So now, is connected 3, 0 will return true. Actually, any of these would be connected, right? So now let's more concretely talk about the interface. So we have these two methods that are the most important, connect and is connected, that will have these expected parameters, where connect connects two items, P and Q, and is connected checks to see if P and Q are connected. So now we have our goal a little bit more clearly, right? We want to define some sort of concrete implementation such that the number of elements, so our n here, can be arbitrarily large, really big, that the number of method calls, so the number of times that we call either connect or is connected, can also be huge. So we're accessing this data a lot. We're not just dumping it in there and leaving it there. And that the calls to either method, so connected or is connected, might be interspersed. So what that means is we could call connect a whole bunch of times and then is connected a whole bunch of times and then alternate one and the other, right? We can't make any assumptions about the order that these methods will be called in, or that any one over the other method will be called more often, right? So we want to just make sure that it is sufficiently efficient in either case. So either if, well, of the three, so either if connect is called all the time, is connected is called all the time, or somewhere in between, right? Some collection of connect and some collection of is connected calls. So the first thing that we want to do is just record things that are connected, right? So if we're connecting two things, why not just record some sort of collecting line and some sort of data structure, right? We've talked about trees, we've talked about graphs, right? So what would it look like then if we were checking connectedness? We would have to do some sort of pass or iteration over all of the lines to see if one thing can be reached from the other. We'd have to check all of the possible paths coming out from one because we don't know anything about how the rest of our components connect together, right? We have to follow every possible path to answer the question, no, they're not connected. So this sounds pretty slow, right? Like in order to iterate over all of our elements, we said that we want to be able to have an arbitrarily large number of elements. That will take, an arbitrarily long amount of time. We don't like that. So let's try to exploit something about the nature of this problem. We're going to step through like a somewhat iterative design process now to try and come up collectively with some sort of implementation that will let us achieve these goals a little bit more efficiently than what we're seeing right here. So now let's think about connected components, what we were talking about before. So how about instead of manually writing out every single connected line, we only record the sets that each item belongs to. So at first, each item would be in a set by itself, right? When we first start with, data or with 7 elements, right? All of them were in their own set. So after the very first line, we would connect 0 and 1, meaning that 0 and 1 are now in the same connected component. So we could just put them in the same set together. Then in the same way, once we add 2, we could add it to the connected set. And the most important thing that we can see here is, even though we connected 2 and 1 together, we're still automatically getting that information that 0 is also connected to 2 because they're all just living in the same set. Whereas before we were drawing lines in between individual elements, now we are just keeping track of sets as a whole of elements. So now we could add 4. And again, in the same way, we see that, we get extra information in this layout because we're not just drawing individual lines, we're putting things into different containers. And we can see everything else that's in that container once we put it in. I guess that's the important part. So we can connect 3 and 5 and we can see that, so we're still representing connected components separately, but we gain all of the information of what else is in that connected component. So the connect 2, 4, they're already connected. So whereas before that would draw a new line, meaning that would take that would record new information and take some sort of computational cycle. For us, we could look in our current representation and say, are 0 and 4 already in the same connected component? Yes, they are. I guess there's no work for us to be done there. That's pretty cool, right? That's kind of a free operation somewhat. So now when we connect 4 and 6, all we have to do is just grab this entire set of 6 and stick it in. But then what do we do when we are connecting a bigger set with some sort of smaller set that's not just one element? we combine everything together. Because once 6 is connected to 3, then that means that there's some path between 3 and 6, which means from 6 we can access anything that's in the same connected component as 5. So we want to take everything from 3's entire connected component and add it to 6's entire connected component, because they're all directly accessible from each other. Okay. So for each item, its connected component is the set of all items that are directly accessible from that to that item. So before we were recording every single connection somehow. Now we are modeling this in terms of individual sets. So how things are individually connected is less important, and we only need to keep track of like each individual's ownership or what is belonging in some specific connected set. Okay, so now we are going to move to the first actual, shall we say, improvement of how are we going to concretely keep track of these connected sets? How do we track membership in Java? So what we're going to try and do now is solve this problem by optimizing each of the operations in our data structure. And the first thing that we'll do is optimize checking whether two things are connected. So quick find means quickly searching through our existing data structure and finding the information. Are these two things connected? Yes or no? So a challenge for all of you, I'd love to see in the chat. So again, the first thing that we want to do is choose some sort of data structure that keeps track of which items are in the same set. So think about it for a little bit and assume that all of our elements are numbered from 0 to n-1. What data structures, think for a little bit, could you think about using in order to represent this information? Great, getting lots of suggestions. Thank you. So something that we could do, which is something that I saw a couple of people suggesting, is storing some map from integer to integer, where the first number represents the set. So the set number, we could order the sets in some way and give them, a unique name or number. And then the second number would represent the item. This would be really slow because we would have to iterate through everything. So let's say we were looking for membership in set 1. We'd have to look through every item in the map where the key of the key value pair is 1. And that's pretty slow, right? We have to iterate through all of them. That's not what we're trying to do. Let's think about something else. So now let's think about a slightly different idea, which is using a set instead of a map, using a set, but having a list of integers with a set as each of the elements in our list. So this is what we will pretty much end up doing moving forward. So we have this list of integers where each index refers to the connected component, and then the set at that index would refer to all of the items in that connected component. So it does still require iterating through the sets to every set to find if two things in different sets are in the same, could be connected, right? Because it depends on how we're adding everything to the sets at each index. So the overall runtime is going to be about linear runtime, meaning we're touching every element each time we are trying to figure something out. So in the worst case, if nothing is connected, then is connected 6, 5, 5, 6 requires iterating through all n-1 sets to find 5 after iterating through all n sets to find 6. So then the overall runtime, it is still linear there. So with a list of sets, the constructor's runtime has to be some order of growth no matter what, because we're having to construct, you know, some data structure of size n, right? So it's going to take about n time. And the worst case of linear is what we came to on the last slide. There, some cases could be better, but you know, we'll say big O because we can say that as an upper bound, as Sohum just taught us. So list of sets is complicated and slow, not quite as slow as the very first implementation that we came up with, but still pretty slow. Most of these operations are linear, especially when the number of connections are small, because you have to iterate over all of the sets. And the most important thing to point out here is because of our decision, because of the decision of what data structure to use as the underlying implementation, so specifically a list of sets, we've doomed ourselves to a specific, you know, complexity and runtime that have not great performance. So this shows really why it is absolutely critical to spend time thinking about what we want to use in our underlying implementation, because it will have very drastic effects on the complexity and performance of our resulting product. Okay, so now we are going to talk about a new and perhaps, as a hint, faster than what we just talked through implementation. So what if we have a list of integers where the ith entry, so let's say the first, or you know, index 1, so the second element gives the set number or ID of item I. So that would mean that for item 2, element 2 is in set 5, which is the name of the set. So that means the value at index 2 is 5. So the index refers to the element itself, and the value is the set number that it exists in. So when we are running this call to connect, it will be to require one array access of changing the value of P to be whatever the value is at Q. So for example, if we were connecting 5 and 6 together, we would update the value at 6 to be whatever the value at 5 is. So this is why it is, shall we say, convenient that we've chosen to represent each of these items in our set as an integer, because now each of these items corresponds to an index, and we can step into an array at a specific index very, very, very quickly. So essentially, we're using an array to map items to their set ID without having to represent a map or some sort of two-dimensional data structure like what we saw with the list of sets. So this is just quickly glancing at the actual implementation for Quick Find. You don't have to worry entirely about like actually understanding this code right here, right now. It's pretty simple, and you could come back and work through it later, looking at the slides if you want to. And we will work up to some new ideas too. But basically, the most important thing is that isConnected becomes very fast. You just have to do 2 array accesses, right? One to check what is the value that I'm going to put in the other one, and then the other to go to that index and put in our new value. But connect itself is pretty slow, right? We're going to have to do a whole bunch of array accesses, which on order of linear. So now we are going to compare the runtime of what we had before. So before we had this list of sets, and now with our Quick Find, we still have the same constructor and connect runtime, but our isConnected is much, much faster. So that's a beautiful new behavior that we get. And it's going to be much more practical to use, right? It'll be much more efficient and realistic to use to solve our problems. So now let's try something more radical to see if we can deal with either of these 2 linear time performances. So now we're going to talk about quick union. We already optimized isConnected, so now let's focus on connect, the method connect. So we lost the connectedness idea at Quick Find. What else was it hard to keep track of, right? Our first approach was just representing everything as boxes and lines. This was really complicated. How do you represent this in instance variables? How could we actually code this, right? Like this is more of a human brain way of viewing it. The next thing we did was our list of sets, where we represented everything as connected components, but then represented those connected components as a list of integers, right? So this is what the list of sets would look like. Then we suggested quick find, which is still representing everything as connected components. And the way that we are representing connected components is a list of integers where the value at that index is the ID or the set that item belongs to. So this is the array that we just had on the last two slides ago. So now we will try to improve the connect operation. So with quick find, everything is connected components. The bad feature for that one, right, is that connecting two sets is slow. So the new approach, quick union, will be representing everything as connected components still, just like the past two implementations. And we will still represent our connected components as a list of integers. However, the values that will be chosen will be smart chosen, right? So we'll put some more thought into what value itself is chosen in order to make connect fast. So think about it. We're about to go to the next slide. So the hard question is, how can we change our representation so that combining two sets into their union requires changing one value only? So going from this half, right, where 3 and 5 are in their own universe, to this side where 2 and 5 are connected. How can we do this with only changing one value? The ID of the set is arbitrary. Yes, it is. Have everything point to the root of the set is something that I am seeing in chat. So we will move forward. So basically, one idea is assign each item a parent instead of an ID that represents some sort of tree-like shape. So having some sort of root is exactly what we were looking for. So as a quick aside, the optional textbook has an item parent as itself instead of -1 for root items. So it would be, the identity instead of -1. In lecture and in assignments, we'll be using -1 just in order to make it clearer. So basically what we're going to be doing is, perhaps innocuous sounding, arbitrary seeming solution that will unlock some pretty cool math that we won't discuss, but that you will discuss in 170, that will allow us, because we're mapping items to their parents, to change far fewer values for each connected call that will get us beautiful runtime. So if we are trying to connect the item 5 and the item 2 together, how should we change our parent list to handle this connect operation? So why can't we just set the ID of 5 to be 2? I'd love to see some suggestions in the chat. I see a great suggestion in the chat, so I guess we will move forward. One possibility would be, instead of updating 5, because if we had updated the position at 5, we would have lost the information that 5 and 3 were connected. So instead, we could have chosen to update the parent of 5, which is 3, and put that below 2, right? So now 3, our item 3 is connected up to the value of its parent, which is 2. So that means that we would be able to trace some sort of line from 5 to 3 to 2 all the way up to our root of 0, and we would know that they would be connected. So that solves our problem of losing the information that 3 and 5 are connected. So find root for 5 would return 3. Find root for 2 would return 0. And so basically what we want to do is set the root of 5, which is 3, to equal the root of 2, which is 0. So we're going to update only the value associated with 5's parent to be whatever the value associated with 2's parent is. So all we will do is updating at index 3 to be 0, because that is 2's parent value. Okay. So what are some potential performance pitfalls with this approach? Unlike with our quick find, we do have to do some steps to climb up a tree, right? We had to figure out what these calls to root were. When we called root 5, it was only one step, right? Stepping from 5 to 3. But when we called root 2, that was 2 steps. And we're talking about, arbitrarily large n. These could be arbitrarily complex trees, right? We don't know how many steps it will take to get to the parent at any given time. That seems like it would be a problem in our runtime, right? So it turns out that it will be really expensive if some tree is too tall, because any call to root will require a whole bunch of steps up, right? So how can we deal with this? So in the worst case, right, if we connected the first item to right below the second item, we will end up with something that looks like a linked list, right, that has height m after m operations. So then for n items, what would be the worst case runtime for some call to connect? Oh, let's see in the chat. Yeah. I'm sorry if you're dead. We're so close to being done. Yeah, so I'm seeing some suggestions. Great. And what about is connected? So for both of these, some of the answers that I saw in the chat were correct, that we will be bound by theta n for both of these operations in the worst case. So now we have this find operation that is the same as root on the previous page, which is going to be where we have a whole bunch of our time sink, right? And so for n items, this means that as we said, we're going to have a worst case runtime of theta n, which is, perhaps not what we want it to be. But for here, we need to use big O because it might not be in the worst case, right? There could be a whole bunch of settings where we don't connect items in such a way that we have a perfect line, right? It's actually, there's only really one insertion order that would give us that perfect line, and all of the other insertion orders would give us something that's, not quite as spindly or long, right? So the general thing is, right, so we're on the right track. But in the worst case, we're doing worse than what we had with quick find, right? Because this is big O of n, this is big O of n, right? Both of those are that's worse than what we had talked about for quick find. But we said that the average case, so long as our trees aren't super unbalanced, it's going to be not too bad, right? Pretty good. So how do we make sure that we prevent these lopsided trees? That is going to bring us to our very last improvement, which is weighted quick union. So now, when we are making a choice, what do I make the new parent, the new root? We're making a decision, right? So if we're combining this tree with height 2, if we're combining, these two trees, we have two options, right? This tree with height 2 and this tree with height 3. Would you guess that we want option A or option B? Okay, good. I see two guesses of option A. So functionally, the most important thing here is the idea of weighted quick union is that we are going to keep track of which tree is bigger, heavier, more weighty, and that will be the tree that becomes our root. So we can see that the tree rooted at 0 here is larger than the tree rooted at 3. So that's why we choose this upper version, right, that still has our tree rooted at 0, because it ultimately gives us a smaller height, right? So our runtime is dependent on the height than if we had chosen the tree rooted at 3 to be our parent. So now another example, right, of that has perhaps a more extreme example, we would not want to make 4 our parent, right, because that would increase the whole height of our tree rooted at 0 by 1. Whereas if we kept 0 the parent, it wouldn't increase the height of our tree at all, right, because we already have a larger height than that. So for weighted quick union, functionally what we're going to do is we're going to keep track of the number of elements in each connected component. So now we can then use that information to make sure that we're always following our new rule, which is that we always want to link the root of the smaller tree to the larger tree. So in other words, we want to keep the root as the larger tree and connect our smaller tree onto it, because we know that that will keep the height as small as possible. So now if we call connect 3 and 8, which entries or indices in parent would change? I've already highlighted the answer for this one for you. So the only thing we would update would be the parent of 6, because 6 was the root of our previous tree. This tree is smaller based on weight, not height. We'll talk about that more in the extra slides, pretty much. And so that's why we would update only the parent of 6 to be whatever the new root, so 0, would be. So we're still using our parent array. Is connected requires no change. The only thing that we would have to do is update how we're doing connected. And there are a couple of different ways of doing this. The most common one is, I would say most common, is to use the value, so the weight itself, rather than -1 in the parent array for the root nodes in order to track size. So instead of the root node's value being -1, it will be whatever the weight of the whole tree is. The other thing that you can do is just keep track of some sort of auxiliary array that keeps track of all of the sizes. So we can think about the performance, right, in the worst case, but we can see that in all of these steps, we're never drastically affecting the size of the tree, right? So these are examples where they are in the very worst case, where the height of the tree will grow as fast as possible. But even then these, when we're stepping through, really large number, not really large, larger and larger numbers of n all the way up to 16, the height of the tree is really not drastically increasing. We're only up to size 4, which is way better than what we saw before. So now we have brought ourselves to something that is somewhere around logarithmic performance. For logarithmic runtime and stuff, that we'll go much more into detail on that in tomorrow's lab. So if you're a little shaky on logs, that's okay for now. There will be a lot more information there. But we have in general much better runtime for these two operations, even as our upper bound. So we're going to get much better behavior than what we saw before, and it'll be more than fast enough for what we want to do. So this slide and the rest of the slides, I would say, are extra for today. But the question is, why are we using weights instead of heights? Why aren't we keeping track of height? The real answer is that it won't make your code that much more efficient to keep track of height instead of weight. And it's much harder to keep track of height instead of weight. And so it's easier programmatically, and it doesn't have that much of an effect on performance. And so we choose to use weight canonically for all of our for all of the implementations that you'll be interacting with in this class. So as I said, path compression is extra. It's something that we can do in order to make our runtime even tighter, but it's something that is not really in scope for this course. You'll learn a lot about it in 170. So that really brings us to the end of our iterative design process, right? The whole idea was we had a whole bunch of different ways to implement some sort of standard disjoint set. By standard disjoint set, we mean we had the same interface, we had the same way of interacting with it, but we were just coming up with new ways to implement it. So the people inside of Plato's cave are seeing the same thing, even though we up in the outside world are changing things, making really drastic, differences and changes. And so ultimately, we ended up on weighted quick union with path compression, which will be more than fast enough for everything that we do. So now we are at the very end of just our brief, friendly suggestion slide that I like to include at the end of all of lectures, of just make sure that you're getting enough sleep. Last week's was about water, make sure you're hydrating. And this week's is about sleep. It is important to have some sort of consistency in your sleep time for a vast majority of adult humans. And it is important to make sure that, you have good quality of sleep when you're asleep. So making sure that you are as comfortable as possible and that you have access to the resources that will let you stay asleep through the night. So that is the end of lecture for now. We will hang out for quite a while, or for some time at the end of this call for any questions that you guys have. I'm sure that today was very fast. Asymptotics in general, and then also disjoint sets can be pretty mathy, and they're also a new introduction to the course. So don't feel self-conscious or bad about yourself if today was kind of a lot of content. We're going to be going through labs on each of these topics. And again, asymptotics is something that is confusing for a lot of students. It was one of the topics that was the most challenging for me when I was taking this course. So be nice to yourself, take some time with the content, and just let it percolate, sit in there for a little bit. And hopefully, with time, you'll get more confident with asymptotics and disjoint sets.
Thank you.
Woo. Thanks everyone for coming.
And yes, you should prioritize sleep. You'll probably end up being more productive in the hours that you spend working if you're well rested, even if they're fewer hours. You can ask clarification questions.
Maybe let's turn off the recording so people can feel comfortable turning on their cameras.